Talk is by Xueyang Song from MIT, and she'll talk about translation-enriched Z2 and U spin liquids. So you have 30 minutes plus 15.
Thanks, Lucille. Good morning, everyone. So I'm a postdoc at MIT, and today I want to discuss some spin liquid, in particular Z2 and U spin liquid, and focus on the translation action in these spin liquids and possible connections to the materials, and also some conceptual discussions in terms of symmetry fractionalization in topological ordered system. So I'll start by reviewing some materials like candidates that we have for spin liquid and highlight the role played by spin-orbit coupling and also the magnetic field in these experiments that make the study of spin liquid with translation symmetry, since this spin-orbit coupling and magnetic field breaks like spin rotation, time reversal, etc. So the remaining most relevant symmetries are translations. So this motivates us to study the translation action in spin liquid. Then I'll discuss the theoretical advancements in characterizing the so-called symmetry fractionalization pattern in topological ordered system and connect it to the action of translation symmetry fractionalization in Z2 spin liquids. As an application, we'll see how this fractionalization pattern guide us to come up with a phenomenological model that explain that may be relevant to the measured large thermal Hall signal in alpha hallucinant trichloride that we also saw in this morning's talk. And later we'll go to one higher dimension in 3+1D and discuss the symmetry fractionalization on both Z2 and U spin liquid, but we'll focus on U spin liquid. And in particular, we show that there is a construction of U spin liquid that where translation acts as the duality group for the electric and magnetic monopoles. So spin-orbit coupling is a relativistic effect for the electrons that couple the orbital momentum and the spin momentum. And in these atoms with a large atomic number, spin-orbit coupling strength is enhanced. So for example, in transition metal compounds where the active orbitals are like 4D or 5D orbitals, the crystal field will first split the electron wave function into two sets of representation like EG and T2G orbitals. And further, we can include spin-orbit coupling. The T2G orbitals will be split into two sets of states characterized by the total angular momentum 3/2 and 1/2 respectively. It is particular for some materials that contain these transition metal compounds, or say rare earth compound with active D and F orbitals, that we have this effective pseudo spin 1/2 at low energy, and they represent a class of materials where spin liquid physics are promising. For example, it was shown by these people that in certain spin orbit coupled system in a so-called 90 bonding geometry, a bond dependent interaction between the pseudo spin 1/2, so forming the Kitaev model, can arise. So the spin orbit coupled effective pseudomagnetic moment enable give some interesting ingredients that may be amenable to search for spin liquid physics. So maybe it's good to mention some concrete material like example, like the candidates that we have for spin liquid at the moment. So the first one is a cobalt-based compound, and the active 5D orbitals like forming an effective 1/2 moment on a honeycomb lattice, and it is found that a relatively small out-of-plane magnetic field suffices to suppress the magnetic order and give a, like, say, continuum in the terahertz spectroscopy transmission, so indicating a quantum spin disordered state. Yeah, there are also like thermal conductivity measurements in this material that hint at a gapless spin liquid state. And the other material, which includes this rare earth ytterbium compound, which is at low energy, is also described by some effective 1/2 moment coming from a spin orbit coupled coupling mechanism, yeah, which is also like studied by the UCSB group. So it is found that it's relatively low disorder, and with T-square specific heat, indicating some low energy emergent U1 Dirac fermion, and inelastic neutron scattering also gives some characteristic critical excitation at the K momentum, which is consistent with a U1 Dirac spin liquid prediction. Yeah, so the third material, which is also focused on today's talk, is the alpha ruthenium trichloride. Again, so you saw this phase diagram. So at intermediate in-plane magnetic field, the spin order is suppressed, and there could be a putative quantum spin liquid regime. So again, it's the ruthenium that gives the effective pseudo-magnetic moment from spin orbit coupling. And here is some example of the neutron spectroscopy. And as one tune up the magnetic field, say at zero field there is a Magnon peak in neutron spectroscopy, and at 7.5 magnetic field, the neutron peak disappears and was rather replaced by a continuum in the low energy. And what's more striking is this large thermal Hall signal that was measured by Feng Ang's group. So you saw it's a very complicated material, and there is still a debate. But for the purpose of this talk, let's probably focus on like Feng Ang's data. So like in this intermediate magnetic field range, where the quantum spin liquid is proposed, a rather large thermal Hall signal is observed, and it shows an activated behavior in that the signal is suppressed as one goes to zero temperature limit. So this thermal Hall signal can be fitted by some Bose-Einstein distribution, so indicating it might be of some bosonic origin. As you can see, so the thermal Hall signal is most like pronounced or like sharp at this intermediate magnetic field, like from 7 to 11 Tesla, right? So from these previous discussions, we see that usually in this spin orbit coupled material and with the tuning of magnetic field, we have the most promising prospect for finding spin liquid, and which already broke much of the symmetry. And so this calls into order the study of the translation, like the remaining symmetry in this theoretical spin liquid states. And as an application, so we mentioned the thermal Hall measurement in leucine trichloride, and the possible origin of this thermal Hall signal has been discussed by lots of theoretical groups as well. So the first candidate is the spin wave, right? Although like it's, if we want to count for the continuum neutron spectroscopy at the intermediate magnetic field, so they might come into question. And like Mengxing also like studied the phonon contribution in this material, and it might also be inconsistent with the large signal of thermal Hall. So if we want to stay in the putative spin liquid story, right? And the pertinent like bosonic quasi-particles that may give rise to these thermal Hall signals is like the so-called Xueyang in Z2 spin liquid. Yeah, for simplicity, we assume, say, it might be a Z2 spin liquid, since like the specific heat measurement also indicating a gapped state in leucine trichloride. Yeah, so next I'll first discuss the translation-enriched Z2 spin liquid and its implication on like this Xueyang dynamics and the thermal Hall effects in alpha leucine trichloride. Here is a preliminary on the spin liquid state that I want to focus on. So it's very similar, like it's basically the we can think of it as the Torrey-Code model, where the low energy excitations have like we have three different types of so-called anions. One is the gauge charge E, and the other is the pi flux of the Z2 gauge, so-called Xueyang. Later we'll both call charge E and the flux as Xueyang. If one fuse E and M, we get a fermionic particle epsilon. So a crucial feature for the Z2 topological order or this kind of Z2 spin liquid state is that if one takes the charge around the Xueyang, a pi barrier phase will be accumulated as like from the definition, right? Like the Xueyang is a pi flux seen by the charge. The study of like the symmetry actions on in these topological ordered states was active in the like past 10 years or so, and there has been already significant advancement. Basically, we have a rather comprehensive theoretical framework to characterize this symmetry fractionalization. So the first important concept is the like symmetry localization that enable one to properly discuss the fractionalization pattern of symmetry actions. So the anions, they are a fractional excitation in that a physical excitation must contain like multiples of these anions. So let's consider like two anion excitation. They are separated and they are linked by some like gauge string. So the action of certain symmetries can be decomposed as the operators with support, local support near the true end of the string, like where the anion lives, and also a in the intermediate region, like formed by these closed string operators. So it was shown that these string operators, they can be their action can be transformed to like identity on the ground state. This makes the most interesting part of the symmetry action localized around these two ends of the string. So in this way, people can talk about the symmetry action on a single anion, it forms a so-called projective representation of the symmetry group, such that the combination of these anions, when they form a physical state, forming a linear representation of the symmetry group. We have from the perspective, say, from the edge theory, to study the allowed symmetry fractionalization in these states. Although, if we want to consider translation, usually the edge break translation, right? There is also more formal framework using mathematical tools to systematically classify the fractionalization pattern. For our purpose, for the application on these spatial symmetries, one probably needs some twist on this mathematical framework to get the answer. And here we adopt a rather physical approach to study the translation actions in Z2 spin liquids. So our strategy is to list all possible symmetry fractionalization pattern, right, with the constraint that any physical state will form representation on the system. And then we either prove such symmetry fractionalization patterns, say, cannot be realized in a purely 2D system, or we find certain theoretical model, right, that realize the fractionalization pattern. In the Z2 spin liquid case, we find that all possible symmetry fractionalization pattern one can enumerate can be realized. We can construct the models to realize such state. So a defining relation for the fractionalization pattern is by taking an anion and translate it along a parallelogram trajectory characterized by T1, T2 are the two elementary translation action, T1, T2, T1 inverse, T2 inverse. And for the this Torrey code example, the only possible option for the fractional either this parallelogram trajectory gives a +1 or -1 phase. Since two anions, they must form a linear representation, so we only have a + or -1 choice. And another twist in the classification scheme is that we also have the scenario where translation permutes the anions, unlike the prototype, say, Torrey code model, right? There are also the models, say, proposed by Xueyang Wen and another certain limit of the Kitaev model, where the translation is realized as a permutation between the electric charge and the Wison, the E and M particle. So here, translation is a very non-local action in that it permutes changes the superselection sector. So in this case, the naive trajectory that we mentioned, T1, T2, T1 inverse, T2 inverse, is kind of ill-defined, right? Because it's involves very non-local action on the anions. So to properly classify this type of Z2 topological orders, we instead find some modified translation in that these are the new elementary translation that preserve the anion type. Say in the Wins plaquette model, we consider the translation along the diagonal direction. And again, say a electric particle moving along this diamond trajectory will pick up a Barry phase if there is a Y-song, background Y-song, right, live inside the trajectory, inside this. Yeah, so another interesting twist also in this anion permuting scenario, right, is that we can, previously we mostly focus on only E and M, because naively you would think the epsilon particle fractionalization comes straightforwardly from the fractionalization of E and M. However, if one, we find that in this anion permuting case, a background fermion will give us some distinct physical SET state, in that it will change the boundary condition in certain particular geometry. So to see this, a physical picture which was discussed in these papers that construct the translation-enriched Tauri-Colt model, where translation permutes the E and M particle, is by decorating on the lattice by these Kitaev chains, 1D Kitaev chains. So a simplistic picture for the Kitaev chain is that each physical complex fermion is fractionalized into 2 Majorana fermions, and the Majorana fermion they form some coupling between the sides. So when say a Y-song, a M particle tunnel through this Kitaev chain, the coupling between these 2 Majorana fermions, right, written like I, epsilon, say epsilon I, epsilon J, the coupling will be modified with a minus sign, since this M particle is a pi flux. It insert a pi flux through the chain, and in this way, the total fermion parity in the Kitaev chain in the ground state, it should be to preserve the total fermion parity. 1 Majorana fermion must be attached to the M particle, and in this way, the M particle becomes a E particle from this fusion rule. So in this picture, if we consider putting a background, say epsilon particle at each side, right? This naively you would say, still if you consider the say diamond trajectory, it is not modified because it always includes some even numbers of the background epsilon particle. So the defining relation for the EM particle and actually for the epsilon particle, they are not modified. However, from this decorating Kitaev chain picture, there is some physical effects by decorating a background Majorana fermion. So the physical effect, if we consider putting the system on a torus with with an odd number, say along certain with a odd size along say the x direction along some large cycle, and then decorating the Majorana fermions will change naively it changes the fermion parity of the ground state, and to preserve the fermion parity, one has to change the boundary condition for this Kitaev chain from periodic to anti-periodic. So this can be probed, say, if one take a Majorana fermion along some large cycle in this torus, it will pick up an extra pi Barry phase and distinguish the states with or without the background Majorana background fermions. After these considerations and the various twists, we come with a complete classification of translation-enriched Z2 topological order, and they are generally classified into 4 types, whether translation preserve anion type or one particular translation permutes anion type, or like class D is both translation permutes the anions. And inside each class, they are further classified by the defining relation, whether it's plus or minus 1. And the detailed model can be constructed by putting appropriate like background electric particle or magnetic particle, visons in the background that gives the desired, say, Barry phase of the defining relation. As an application, the thermal Hall effects coming from this Wison band is given by the Barry curvature like of the Wison band, and for a simplistic like one band Wison model, if the defining relation is trivial, one can prove that this one band model have a total vanishing Chen number and unlikely to give a very large thermal Hall signal. So we need to look for large thermal Hall signal from the spin liquid states with this frustrated defining relation. And hence, we consider a phenomenological model pertinent to alpha and trichloride on the honeycomb lattice, where there is a background E and M particle. And another interesting feature in this model is that translation permutes the two Wison types. Without very hard fine tuning for the Wison, like hopping and pairing model, we can give a thermal Hall signal that is comparable to the experiment data. And the reason we consider a translation permuting model is that at low energy, the material fall into a zigzag order, which preserves one translation and breaks the other. So a putative, say, second order transition from the spin liquid regime to the ordered state here can be accomplished by condensing one of the Wisons, say, say the E particle. And due to the translation permuting these anions, once E particle condense, the translation along, say, this T2 direction will be broken. So this naturally gives the zigzag order. Yeah, so we show like that the symmetry fractionalization and also coming from the universal physics of the Barry phase between E and M particle allows us to engineer towards the Chen bands, Wison bands with non-trivial topology. So next I want to quickly flash out the case for 3+1D spin liquid. Yeah, so we can similarly classify like the Z2 spin liquid, translation fractionalization in Z2 spin liquid. And more interestingly, I want to focus on U1 spin liquid in 3+1D, which is described by the emergent quantum electrodynamics. And from like classical from like the Maxwell equation that we learned, there is a manifest symmetry in Maxwell equation, which is by sending E to B and B to minus E, and forming the so-called electromagnetic duality. And actually, this duality can be extended into the a full group with the group structure of a special, so-called special linear group. And the action of this full duality group can be thought of as acting on the charge lattice, where each quasi-particles in the U1 spin liquid, they are labeled by the electric and magnetic charge. So they are labeled by two integers. And the duality group acting as a like SL2Z matrix on these coordinates in the charge lattice. So I'll show you like how we can construct like the models that realize such a duality transformation by translation, like for example, along Z direction. And you saw in Xie's talk yesterday that this similar construction by stacking layered integer quantum Hall states. Like here, the integer quantum Hall states for the electric charge in the emergent QED. So in this case, once we take a monopole, which is the source of the 2-pi magnetic flux, tunnel through this integer quantum Hall layer, it will thread a 2-pi flux in the integer quantum Hall layer and nucleate a 1 electric charge. So in this case, the monopole gets attached with a electric charge upon the translation. And we realize another duality that is so-called the T duality. So it's actually related to like this fracton phase in yesterday's talk, in that if we take the charge gap to infinity, monopoles are forbidden to tunnel through the layers, or we take the decoupled layer limit. And in this case, like the monopoles, they are like the fracton excitations. And to realize the electromagnetic duality, we have very similar construction. Although here at each particular layer, we stack like 2 different quantum Hall states, like from the dion, 1-1 dion, and the quantum Hall states for the charge. Yeah, it takes some simple exercise to see that both the magnetic monopole gets transformed into a electric charge, and the electric charge gets transformed into the magnetic monopole once they tunnel through these 2 integer quantum Hall layer. So yeah, here is a cartoon picture in that in stacking these quantum Hall layers, the electric charge is translated into a magnetic monopole upon tunnel through the layers. Yeah, so there are some also connections to the like in the formal aspects of the like field theory literature. So there is a discussion of a topological wall operator that realizes this S and T duality. Essentially for the T duality case here, we are it's equivalent to stacking this topological wall operator as like stacking each integer quantum Hall layer. We also have some like open questions, like for example, the realization of such model in like realistic, say, lattice model, quantum spin ice, say, states. To study, like there may also be interesting dynamics once we tune up the interlayer coupling. The state may evolve from some like in the decoupled limit, decoupled chain insulator limit, to some states with say spin non-forming surface spin liquid state. Yeah. So to summarize, we study like the translation fractionalization pattern that enrich the topological order or like the spin liquid states. I want to emphasize like the role of coming from stacking lower dimension topological, so-called symmetry protected topological phase, say Kitaev chain or like integer quantum Hall layer. That is crucial to study the fractionalization pattern and also give us interesting action that permutes the quasi-particles in this spin liquid state. Yeah, thanks.
Thank you very much. Are there any questions?
Hi, can you go to the last slide of your 2D, the end of the 2D? Yeah, the one after that. So I understand how if you break translations through the 3 direction, then so if you condense like E anions, you break translations through the 3 direction, and you should get a zigzag order, but I can't see how to do it if you do it in the one direction. So like, can you get zigzag orders in all three directions from different kinds of condensation?
You're right. So for a particular, say, permutation, anion permutation scenario, yeah, we break some particular translation. And so this particular direction is selected by your magnetic field direction. Right?
Oh, right, it's an in-plane field. I see. Okay. Yeah. So the spin liquid breaks C3 symmetry, so it picks one direction. I guess.
Yeah, C3 symmetry, yeah, it's already broken.
I see.
Yeah.
Thanks.
Thanks for the nice talk, Xueyang. So I want to understand the example with decorating Kitaev chains a little bit better. I guess in this case, do you start with a system where translation permutes E and M, and then you want to so is that the sort of situation that I want to think about?
Right. So it is like rather by decorating this Kitaev chain that the translation is realized as a permutation. Yeah. Of
I see. Okay. Yeah. Okay. That makes more sense to me. So the idea is we put down some Kitaev chains and then gauge the fermion parity. And then this is just a description of what happens in the resulting Z2 gauge theory. Is that right? So we start with a system with no dynamical gauge field.
Right.
Put down some Kitaev chains, gauge the fermion parity, and then this is a description of how the M excitations move around.
Right. Exactly. Yeah. That's what's discussed in this paper.
Yeah. Okay. Good. Thanks.
Okay, thank you. Can you go back to the slide of your symmetry fractionalization table? Yeah. So all of these fractionalization patterns are realizable in pure 2D like Z2 spin liquid, right?
Yeah.
Is there any like indicators of whether something that's like some realization of the translation symmetry might be anomalous, like whether there's such an indicator in your theory?
So yeah, as we there is explicit construction for the models that realize each of these class in 2D. That's a purely 2D model. Yeah. So there shouldn't be anomalous anomalous pattern.
Yeah, but I'm just saying that, like for example, like I throw you a set of like phases, like 1 or -1. Can you tell? Like, is there a way to tell whether these phases are realizable in a pure 2D system?
You mean like for some general, say, other symmetries?
No, I was just talking about like the two translation symmetries. Like if I give you a random like pattern of fractionalization.
So yeah, here as long as the pattern of fractionalization they obey like any physical state form a linear representation, right? Obey this constraint. They can be realized in certain 2D model.
So
so the logic is we list all possible fractionalization pattern that's consistent with the constraint, and then it is found that all these fractionalization pattern can be realized in certain model, like building from say Wien's plaquette or Torrey code model, or like decorated Kitaev chain model. Yeah.
Okay, so there's no something like let's say an ETMT state that cannot be realized. So such state doesn't exist in the fractionalization of translation symmetry.
No, in only translation-enriched topological order, we didn't find such anomalous states.
Okay, sure. Thank you.
So I guess I have a naive question. Can you have patterns other than this that have, say, larger unit cells? Like instead of doubling the unit cell, you triple it, or have a 10 times larger unit cell or something like that. Because like here you have your new translation symmetry is like T1 squared. What if it were cubed?
Right.
Or something like that? Is that possible? Is that different from this?
So in this Z2 states, the anions, they have like they have finite order, right? Like yeah. I suppose I can't imagine there are other like say the anion permutation like that has a larger periodicity, say 4 or 8. Like given we only have two anions, two bosonic anions, right? That can be permuted.
I think I might be asking a dumber question, actually. Like, so just looking at the patterns, right? I could imagine, if I'm just thinking of like E and M as two things that I can lay down as a pattern in 2D, I can make things that have larger unit cells, right? So why are those not
respecting translation, right?
In translation, right? So I can do like E-E-E-M or something like that.
Then it's hard to define a consistent translation action, right? Your translation action, say, if you are saying on the line, say E-E-E-M, then translation didn't permute, like preserve the E type for the first 3 translations, and for the first one,
I see. So it always has to permute as for every single translation. You can't just make big unit cells.
Yeah.
Okay. All right. Thanks. I figured it was done.
So I'm trying to understand. So for this, to have a Wison band with non-trivial Chen number, I assume it's not a universal feature of any particular symmetry fractionalization pattern, right? So you mentioned that you don't need too much fine tuning. So how much tuning do you actually need?
Yeah, so the tuning is in the pairing part. So we have complex pairing to break time reversal. Yeah, so it's kind of some P wave or D wave pairing, I think, in this case. So I think that's the crucial part to engineer for Chen bands.
I see. So you're basically putting some flux in that delta, and that's it.
Yeah, and of course it's a frustrated hopping, right? Because there is background anion. So for T, they have to satisfy some frustrated hopping pattern. Yeah.
Okay, thanks.
So do you know what happens when the magnetic field is rotated? Because it seems like this pattern, because it breaks C3, when you rotate the magnetic field, I would think you would have to have a phase transition between different kinds of spin liquids related by C3.
So there are distinct spectral, like data, say for magnetic field along A and B axis. And by C3 is like rotating from A to B and then again back to A axis, right? Magnetic field.
I see.
So
I guess I mean, like, as you go from the A axis back to this C3 related A axis.
Right.
So that means the pattern here will have to change to its C3 image, which is a distinct state.
Right. Yeah.
So there'll have to be a phase transition in between. Is that right?
Yeah. So there may be multiple phases, as I say.
I see.
In between there is a magnetic field along B axis.
Oh, I see.
Yeah. So the phenomenon, like along B axis, it might be a gapless spin liquid, like from specific heat data. Yeah, but purely theoretically, like the model, like with different anion permuting pattern, right, is they should be separated by some phase transition. But yeah, it might be interesting whether like to see if can be a second order phase continuous transition.
Thanks.
One last one.
Hi, thanks for the nice talk. So just a simple question. So here, do you have have some idea how the parameters T or delta are related to microscopic parameters of the spin model?
Yeah, that's very good question. No, we don't have any. Like there are papers by like Inti Zonderman that are able to extract the low energy like effective Xueyang model from some microscopic spin Hamiltonian construction. Yeah, so there might be a way to infer the relationship, but yeah, here I don't have a very straightforward answer like the any quantitative relation.
Okay, thank you.